Now talking about the JFET biasing again. This is a continuation of the previous video about JFET. Welcome to your TipsKnowLogy again. For the JFET biasing, let's talk about the Q point. You will see here on letter A the sample circuit of a JFET connected or the N-channel JFET connected in a circuit here. And you take note that the VG is equal to 0 volt and there will be current here, we call it IS. Now setting the Q point requires us to know a value of RS that will give us whatever desired current on the drain and the VGS that we want. So the formula below will show you the relationship. So RS is equal to the absolute value of the VGS divided by the ID. And to be able to do this, we must first determine the VGS and the ID from the transfer characteristic curve, or more practically, from the formula given. So the datasheet provides us the IDSS and the VGS off. So if you want to know the IDSS or if you want to know the VGS off, you can look at the datasheet of the JFET. On the other hand, the VGG is representing the voltage or the voltage that we desire to set on the bias or on the JFET biasing that we are doing. So again, this is the called transfer characteristic curve here. And this along any point along this curve is what we call as the VGS. So from 0 to a certain VGS on the x-axis. And upon reaching the IDSS here equal to 0, that's called VGS off. And again, if the VGS off is -7, then it's like we also know the VP, which will be positive 7 volts. So by the way, the ID is equal to IDSS multiplied to 1 minus VGS divided by VGS off to the second power. So now we move on with some examples of calculations. Let's say we want to determine the value of the drain current for the circuit below. When we say drain current, it means we want to know the ID. And the formula that we will be using is IDSS multiplied to 1 minus the VGS divided by the VGS of close parenthesis and raised to the second power. So our IDSS here is given as 3 milliamperes multiplied to 1 minus the VGS, which is 2 volts. Take note that although this is written as 2 volt, we have to consider negative because of this negative connection. So negative 2 volts divided by negative 6 volts raised to the second power, and we will be getting 1.33 milliamperes. So for those who don't know, VDD means the voltage supply at the drain terminal, this one, VDD. In this drawing, we did not put any more a voltage source symbol here. We simply put here a small circle symbol with VDD. So this represents the voltage supply at the drain terminal. Now the VGS is the gate to source voltage or the gate source voltage. VGS off, this is also the pinch off voltage. So the VGS off is -6 volts or the pinch off voltage is -6 volts. IDSS means drain to source saturation current. Again, if this question is given to you like determine the value of drain current for this kind of circuit, this is the formula. Now for the second problem, we have a JFET here which has a VGS of equal to -4 volts and IDSS equal to 12 milliamperes. These are given, VGS off and IDSS. Now we are supposed to determine the minimum value of VDD needed to put the device in the constant current area of operation, or the cut-off operation. So let's see the calculation. Because we are given a VGS of minus 4 volts, therefore, as we have mentioned in the previous video, that when the VGS off is minus 4, the VP will be equal to 4. So we just copy the number 4 and make the negative to become positive. The minimum value of VDS for the JFET to be in its constant current area will be equal to the following. So VDS is equal to VP is equal to 4 volts. Now in the constant current area with VGS equals 0 volt, the ID will be equal to IDSS, which is equal to 12 milliamperes. So whenever the VGS is equal to 0 volt, here the VGS is 0, the ID will be equal to IDSS. And the IDSS is given in the problem as 12 milliamperes, so ID is equal to 12 milliamperes. Now the drop across the drain resistor, or if we want to calculate the voltage here, we call it VRD. We just multiply it using Ohm's law, IR. So we multiply ID by RD. So if your ID is 12 milliamperes, multiply it to 560 ohms, we will get an answer of 6,700, around 6,720 millivolts. But converting it to volt, that will be 6.72 volts. Now, applying Kirchhoff's law around the drain circuit here, we will see that the VDD will be equal to VDS plus VRD, or we say VRD plus VDS. So 4 volts for VDS plus 6.72 volts for the VRD. So the VDS is equal to 4 volts, as we have mentioned at the beginning, that when VGS off is equal to minus 4 volts, the VP is equal to 4 volts. Therefore, the voltage VDS will be equal to 4 volts. Plus 6.72 equals 10.72 volts. Now, this is the value of the VDD. To make the VDS here between the drain and the source equal to VP. So that's the question here. Determine the minimum value of VDD needed to put the device in the saturation point. So that will be equal to 10.7 volts. Now let's say another example here, that we have a data sheet of the 2N5459 JFET. This indicates that typically normally the IDSS given in the data sheet is 9 milliamperes, and the VGS of equals to minus 8 volts maximum. So using these values, we will determine the drain current. Of course, if the VGS is equal to 0 volts for here, for VGS equal to 0 volts, the ID will be equal to IDSS, which is equal to 9 milliamperes as given in the question. Now for VGS, which is when it is equal to negative 1 volts or 1 volt, of course, when the VGS is negative 1 volt, you will see here in the formula that IDSS multiplied by 1 minus VGS over VGS of negative 1 over negative 8 here, and you subtract it from 1, we will get minus 1 over minus 8 as minus 0.125. So 1 minus 0.125 is 0.766 when it is also taken to the second power. So 1 minus 0.125 to the second power will be equal to 0.766. And then when multiplied with 9 milliamperes, we will get 6.89 milliamperes. So this is the ID using the same formula that I have given before. IDSS multiplied to 1 minus VGS over VGS of raised to the second power. Again, the second power here is raised after we calculate 1 minus this, not after calculating everything. So for VGS, when it is equal to minus 4, let's just substitute minus 4 to our VGS formula here. So the answer will be 2.25 milliamperes. So as you can see, the VGS is 0. We have 9 milliamperes ID. VGS is minus 1. We have the ID equal to 6.89. So when the VGS is 0, 9 milliampere, when you make it minus 1, it becomes lower, 6.89. And when it's minus 4 volts, the VGS, then the ID becomes much, much lower to 2.25 milliamperes. Now, let's talk about midpoint biasing. So since midpoint biasing is the most common, let's determine how this is done. So the first step is that the values of RS and RD determine the approximate midpoint bias. It means that the RD that you put here and the RS will be the one that will control or will determine where or what will be the approximate midpoint bias. So half of IDSS would be, of course, the half of the ID here or the IDSS point here will be the ID midpoint. And the VGS, to establish this, can be determined by the formula here that VGS is approximately equal to VGS of divided by 3.4. Remember, this formula is for midpoint biasing. And the 2ID will be equal to IDSS, or the double of the ID will be equal to IDSS when VGS is equal to VGS of divided by 3.4. Now, the values of RS needed to establish the VGS can be determined by the formula RS is equal to VGS over ID. So RS is equal to VGS over ID. And if you got a negative number, just take the absolute value. And the value of the RD needed can be determined by taking half of the VDD, or VDD divided by 2, divided by again by ID. So these are the RS here and the RD to design such a JFET biasing. Now, JFET biasing summary, remember the purpose of biasing is to set a point of operation or Q point, and in a self-biasing type JFET circuit, the Q point is determined by the given parameters of the JFET itself and the values of RS and RD. Setting it at a midpoint on the drain curve is the most common. And one thing not mentioned in the discussion was RG. Its value is arbitrary, but it should be large enough to keep the input resistance high. So you can use any values for RG, but make sure that it's large enough to make the input resistance still high. Now, for graphical analysis, you will see here on the x-axis negative VGS and the y-axis ID. And at the highest point of the curve, we call this as the IDSS. Let's say this is 10 milliamperes. And in the middle part, we call this as the Q point. Let's make it around 5 or 5.07 volts here. This is the Q point. And then if you take the middle point of this, that's at around 2.3 volts negative and 5.07 milliamperes here at this point. Now, the ID is equal to, that you will get here, will just be IDSS divided by 2. So if this is 10, this is at around 5. And the point here, directly here from this point, intersecting this middle point here to 0, the intersected value here, number 2, you will see is equal to negative 4.7 volts. And this is what we call as the load line for our JFET. So the transfer characteristic curve along with other parameters can be used. When say parameters, the other values here, IDSS, ID, VGS of can be used to determine the midpoint bias Q point of a self-biased JFET circuit. First, determine the VGS, this VGS at IDSS from the formula VGS is equal to negative IDRS. And you will be able to determine the VGS. And then, number one, the VGS here from 0 is equal to negative IDRS, or that will be 0 multiplied by 470, of course, that will be 0. That's number one. And then number two, we have the VGS negative IDRD at 10 milliamperes from here, multiplied by 470, we will get negative 4.74. So from this point to this point, draw a line and you will intersect the approximate value of your Q point. Where the two lines intersect gives us ID and VGS Q point needed for midpoint bias. Note that the load line extends from VGS off to VP. So from here, where the VGS is off to a VP here, that is around negative 4.7 volts. Now let's determine the value of RS needed to self-bias an N-channel JFET that has the transfer characteristic curve shown in the figure below at VGS is equal to negative 5 volts. So from the graph, we can say that the ID is at around 6.25 milliampere when the VGS is negative 5. So to calculate the RS, just divide 5 divided by 6.25 milliamperes, and if you get negative, just get the absolute value and we will get around 800 ohms. Another problem here is to determine the value of RS required to self-bias a P-channel JFET with the IDSS equal to 25 milliamperes and VGS of 15 volts. And VGS is to be 5 volts. So the ID here will be equal to IDSS multiplied to 1 minus VGS over VGS of raised to the second power. So IDS is 25 milliamperes multiplied to 1 minus 5 over 15 raised to the second power. After subtracting this, that will be 1 minus 0.333 without any unit raised to the second power. And the answer will be 11.1 milliampere. So this is for the P-channel JFET. Whereas the one that I have shown you before is for N-channel JFET here. It does not say P-channel JFET, but when we do that, then you will see here, this is the N-channel JFET, even in the diagram. But for the last example that we have talked about, this is given here, N-channel also. The other one was given as P-channel JFET with IDSS equal to 25. Now determine the RS. The RS will be equal to V over I. So the VGS is 15 volts. VGS is 5 volts divided by 11.1 milliampere. We will get 450 ohms. Now for the JFET biasing, which we call as voltage divider, you will see that the voltage divider can be used to bias a JFET. And the R1 and R2 here are used to keep the gate source junction. So the gate and the source junction in reverse bias. Now the operation is no different from self-bias, and determining the ID and the VGS for the JFET voltage divider circuit with VD given can be calculated with the following formula. So for the source voltage Vs, we just multiply ID by RS. If you want to calculate the gate voltage VDD, we can calculate the gate voltage VG. We can calculate it by dividing R2 over R1 plus R2 multiplied by VDD. I think this is similar to the previous example that I have given you about BJT, where we are calculating the Thevenin's voltage as R2 over R1 plus R2 multiplied by VCC. But here, we are multiplying it by VDD because this is for the JFET biasing. Now, for VGS, we just subtract VG minus VS. This is the gate to source voltage. For ID, it's only Ohm's law, VS over RS. So the voltage on the source divided by the resistance RS. So that will be the drain current. So the another formula for the drain current is to subtract VG minus VGS. So VG minus VGS, that will be our VS, of course, and divided by the RS. So that's the drain current, two drain current formula. Now, on the next example, we determine the ID and VGS for the JFET with voltage divider bias in the figure, and given that for this particular JFET, the internal parameter values are such that the VD is equal to 7 volts. So to calculate that, you just subtract VDD minus VD over RD. And VDD is 12 volts minus VD, which is 7 volts, divided by 3.3 kilo ohms, which is the RD. And we'll be getting 1.52 milliamperes. So to calculate the gate to source voltage, we will have to do the following. Vs will be equal to ID multiplied by Rs, or to Rs. That will be 1.52 milliampere that we take from here, multiplied to 2.2 kilo ohms, which is given here. The Rs, that will be 3.34 volts, because the milli is 10 to the minus 3 and the kilo is 10 to the 3. So the 10 to the minus 3 and 10 to the 3 will cancel each other. Now the Vg is equal to R2 VDD over R1 plus R2. So 1 mega ohm for the R2 divided by 6.8 mega ohm plus 1 mega ohm, that will be 7.8 mega ohm, multiplied with VDD of 12 volts. So the answer will be 1.54 volts. For VGS, we just subtract VG minus VS, and we will be getting 1.54 volts minus 3.34 volts. Therefore, if your VG is wrong and your VS is wrong, then your VGS will also be wrong. It's like a domino effect. So the answer for VGS is negative 1.8 volts for VGS. So the transfer characteristics can vary or can be different for JFETs of the same type, just like the beta of a transistor, and this will adversely affect, or the effect will be big for the Q point. So the voltage divider bias is less affected by this than self bias. So this effect of transfer characteristic that can vary for JFET of the same type. So this is an undesirable problem. We don't like this, but in extreme cases, it would require trying several of the same type until you find the one that works within the range of operation. Now the Q point instability. So you will see here the shaded areas between the Q1 point and the Q2 point. This is the variability of Q point, which changes in the transfer characteristics, or GM, of a selection of replacement JFETs. So self-bias will exert no control over the transfer characteristics, or GM, variability. And the voltage divider bias offers some improvement. Now, in the next video, I will be just talking about MOSFET. But for now, I will post this video, and I hope you will subscribe to this video, like this video, and subscribe to our channel towards our goal of reaching 1,000 subscribers. Thank you very much from ERC TipsKnowLogy.